I'm not a Platonist. I don't believe that there is a mirror of reality which is completely expressed by some bit of mathematics, which is precisely equivalent to the universe as is. That seems to me really silly to believe that, but I did myself believe that for a long time. And a lot of people who do what I do or did also believe that. And I think it's a kind of fantasy. I think that's the right word for it. It's a kind of fantasy which elevates your view of what you're doing when you're doing physics or mathematics.
Hello, this is Robinson Erhardt, here with the introduction to Robinson's podcast, number 148. And this episode is with Pins, as usual, and also a very much requested, very exciting guest, Lee Smolin, who is a founding and senior faculty member at the Perimeter Institute for Theoretical Physics. I don't know why only on the podcast I cannot say physics or astrophysics, which always comes out as astrophysicists. But it is indeed the Perimeter Institute for Theoretical Physics. And he is also, quite notably for the show, and some past guests like Tim Maudlin last Sunday, an honorary fellow of the John Bell Institute for the Foundations of Physics. So Lee is best known in the physics community for contributions to quantum gravity, more particularly as a co-inventor of loop quantum gravity and deformed special relativity. But beyond this and other technical work, Lee has written a number of best-selling and great books, the most recent of which is Einstein's Unfinished Revolution, The Search for What Lies Beyond the Quantum, which came out in 2019. And another book that we speak about at length in this episode is The Singular Universe and the Unreality of Time, which he co-wrote with the esteemed Harvard legal scholar Roberto Mangabeira Unger, who likely is evidently a man of many talents. But for the most part, I think it's safe to say that everything in this episode is unified by one particular quality of Lee's philosophical perspective on physics, and that is realism, or as I might put it quite roughly, putting words into his mouth, the belief that there's a single determinate universe. And while that's vague, I mean it in opposition to, say, like a multiverse or various mind-dependent worlds, or even a Copenhagen-esque, uncertain, indeterminate quantum mechanical universe. So we first talk about realism in quantum mechanics, so touching on Bohr, an anti-realist, the many worlds interpretation, which Lee labels as magical realism, and then a bona fide realist, if ultimately unsatisfactory for him, account in Bohmian pilot wave theory. Then we move on to Lee's picture of what an ultimate theory might contain, and we finish with a discussion of the foundations of mathematics, as well as a bit of what it's like living with Parkinson's disease. So some last words. You should absolutely check out Lee's books if you haven't read them. And I particularly loved Einstein's Unfinished Revolution because it very nicely lays out the landscape of quantum mechanics and the various theories or interpretations thereof, and it's quite friendly to somebody who isn't a trained physicist. And also, if you're longtime listeners, you'll know how wonderful the John Bell Institute and its members are. And they are in serious need of donations to make sure that there's a home for the foundations of physics. And I've donated, and I, again, if you're able and interested, suggest that you consider doing the same. And along with Lee's books, there is a link to the JBI in the description. So now, without any further ado, I hope you enjoy this conversation as much as I enjoyed having it with Lee. As I was reading your books, I saw one that you went to Walnut Hills in Cincinnati, which is where my dad went. But then also that you dropped out from Walnut Hills and that you you found yourself, I think, at the University of Cincinnati Library reading books on de Broglie and pilot wave theory. And I was just wondering, before we get into the physics, how it was that you ended up dropping out of high school only to become a very serious physicist, because that's not usually the high school dropout trajectory.
Right, although you'd be surprised. No, what happened is that I was part of starting what we called in those days an alternative school or alternative high school. And the alternative school was based on a philosophy which they explained to us before the as the semester was beginning, that they saw their job as helping us to locate somewhere in the community was the knowledge that we wanted, and then seeking and joining that community or visiting that community. And I thought about it overnight, and I realized the community that held the knowledge that I wanted was the university. So there was no reason to spend a year, except maybe to get kissed by the French teacher, but that's another story. There was no reason to spend a year there in the school. My mother was a professor at the University of Cincinnati. As it happened, she was a playwright. And so I was able to take courses for free. And so I just jumped right in. And so and then the other thing that happened is I got interested in Einstein's writing. Well, I had previously gotten very interested in architecture, and in particularly in the architecture of, and this is where the Parkinson's is going to come in awkward. Particularly in the architecture of J. Buckminster Fuller, if you've heard of him, who was an architect who built with geometrical shapes like triangles and so forth. He built the geodesic domes that are very famous. And I got interested in that kind of architecture because my father wanted to be an architect. He didn't become one, but it was his lifelong ambition. And therefore, he let me know when Buckminster Fuller was coming to our city, to Cincinnati. And I invited him to give a talk at our school, and that's a long story. But I had contact with him. And so I started to learn geometry. It happened that I was early in my studies of geometry, so I was able to do advanced calculus. And I went to the library and got books on advanced calculus because I wanted to make building surfaces which were curved. And every such book contained a chapter on Einstein's theory of relativity, because that was the most beautiful application of that kind of geometry. So one evening, I was stood up by a date, and as I was waiting for her for a long night, sitting on my parents' porch, I read an autobiography by Einstein, and he explained why he wanted to be a physicist, and I found that very appealing. So I overnight switched into wanting to be a physicist. And that put me, I dropped out of high school, of course, but that let me jump immediately to a graduate course in Einstein's theory of relativity that was being taught at the university. And so I took that course. I had the exposure of Paul Esposito, who was a good teacher. And I just decided to jump in and try to go to university and learn to be a physicist. And I was very, very fortunate that I was taken by a very good university, which has just been founded, which was Hampshire College.
Yeah.
And I had a very good physics teacher there, who was Herbert Bernstein. So I turned out to be very lucky and have a good start of a career.
Yeah, Hampshire's a very interesting place. One of my cousins went there, and I know that he loved it. I mean, it's the epitome of the experimental school.
Yeah, I'm afraid it's not doing as well as it did in past years, but that's again another subject.
Mm-hmm. Well, setting aside architecture for the moment, I just finished reading your latest book, Einstein's Unfinished Revolution. So all these years later, Einstein is still very important to you. And what I took from that, or one of the things that I took from that, is that one of your chief appreciations for Einstein was his commitment to devout realism concerning quantum mechanics. And that seems like the right place to start, because I've read some of your other books, and realism is what underpins your views on quantum mechanics, time, cosmology, probably more than I'm not listing. So I think understanding this term as you use it is where we need to begin. So am I right that roughly you take it as your starting point that there is a mind independent world, and this is a necessary assumption for science?
Well, it's interesting. I've been thinking we have to put a separate category on realism and minds, because I have been thinking about that lately. But without going into rethinking pantheism, panpsychism, let's say, yes, I am a realist as far as nature is concerned. And I believe that the purpose of science is to give us the truth about nature, to give us what John Bell called us the beables. And I don't believe that quantum mechanics does that.
Yeah, I just talked with, there's actually an episode coming out today with our mutual friend, Tim Maudlin, that is all about John Bell and beables and observables and Bell's theorem. But maybe a good place to start is that you write in Einstein's Unfinished Revolution that humans have always had a problem conflating reality with fantasy. So we often confuse our stories about or descriptions of what things are like with the real thing. And these are my words here, not yours. But maybe mathematics is a good example, in that many people, I think, mistake our quite useful talk of numbers and sets and functions as meaning that there's some real universe out there that contains just these things. But the reason I bring this up right off the bat is I wanted to start by asking how fundamentally you see the relationship between physics as a collection of stories and equations on the one hand, and then the world.
Yes, well, I don't believe that I'm not a Platonist. I don't believe that there is a mirror of reality which is completely expressed by some bit of mathematics, which is precisely equivalent to the universe as is. That seems to me really silly to believe that, but I did myself believe that for a long time. And a lot of people who do what I do or did also believe that. And I think it's a kind of fantasy. I think that's the right word for it. It's a kind of fantasy which elevates your view of what you're doing when you're doing physics or mathematics.
So much of Einstein's Unfinished Revolution is concerned with realism and quantum mechanics. So maybe before we turn to how a realist can make sense of quantum mechanics, what are some of the phenomena at home in the microscopic that at first glance pose the biggest problems for the realist who's accustomed to seeing the world in a classical sense?
Well, as you hint, the most difficult issues for realism have to do with violations of locality. Quantum physics is definitely not local. By local, we mean that all the forces propagate at a finite speed, and they propagate through space, and that's what causes things to happen. You don't have something happen here and then happen here and then happen here and so forth. And I think if one restricts oneself to that kind of reality, one can't explain quantum mechanics, because I think that quantum mechanics violates that kind of reality, and that's what Bell's theorem tells us.
There are a few. So you mentioned non-locality. There's also entanglement and contextuality. Those are two other major issues that you touch on for the realist. So maybe we could talk about first what entanglement is and why that's a problem for the realist.
Entanglement is the feature of the world where if you take two systems and interact them with them and then let them separate, it may be that the two of them together share some definite property which neither of them apart demonstrates any definite property concerning. So I think that's as good as a definition of entanglement. And the other one is a little bit harder to explain. So maybe can we skip it at this point and simply say that, what is it called? You just used the word.
Contextuality.
Contextuality is up to a small subtlety and application of non-locality.
And then, so given these three features, apparent features of the quantum world, so non-locality, entanglement, and contextuality, there are a couple of early realist accounts of quantum mechanics that make sense of this. So I have in mind de Broglie, but since other quote unquote interpretations of quantum mechanics have been dominant, and they're, I think, the main focus of your thinking in the book we've been discussing, because they sort of set back developments in physics as you see it. What do you think of as the most dominant of these anti-realist views? And then what is it about them that qualifies them as anti-realist?
Well, the most dominant one, of course, is just incoherence. People don't think things through that they teach or read. That was supposed to be funny. Who is the most dominant? A lot of people like to believe that they espouse the many worlds interpretation. But again, that's a very subtle interpretation. You can give it a very science fiction-y character. That's not really what it says. And basically, I think it's equivalent to a badly thought through version of Bohm's theory. But
Oh, really?
people don't like to say that. But let's take the science fiction version, because that is the version that Bryce DeWitt, who was one of the founders of this area, espoused. That is to say, when we asked him, you don't really mean that you think that just in a totally science fiction way, there are all these other universes out there right now? And he said, yes, that's what I mean. And then smiled. So, and I think that it's created a lot of problems for the theory and for science in general, because when you have a bunch of smart scientists going around saying things that are kind of silly, I think it makes the whole enterprise harder to take seriously. So I think it's a problem. Now, to make sense out of the many worlds interpretation, you can't just espouse it. You have to explain how it is that when we observe the world, we see definite frames of reference. That is when we don't see the world in an arbitrarily chosen state or background consisting of any basis element you choose. We see the world only as something going on situated in a classical entity. And that requires explanation for if you're a Bohmian. Another way of saying that is that Born's rule, which is the rule that the probabilities predicted by quantum mechanics have a certain relation to the wave function. They're the absolute value squared of the wave function. And this is not a theorem of quantum mechanics. It's not an assumption either of the many worlds interpretation. So if you think you believe in the many worlds interpretation, you have to explain why it is that every time you make an observation, you see that precise probability proportional to the square of the wave function, and not some other basis chosen probability. And so whether you think that there is a many worlds interpretation depends on whether some quite subtle arguments given by some very smart philosophers, mostly in Oxford, have succeeded.
Many Worlds has come up a few times on the show so far. I recently did a joint episode with David Albert and Sean Carroll, where pretty much all we talked about was many worlds, though fine tuning and then Boltzmann brains came up as well. But something
They're
that
both
I got
very smart.
Yeah, they're both terrific. But something that I got a chuckle out of every time I saw it in your book was that you refer to many worlds as a view of magical realism. That's where it is situated in this landscape of realism and anti-realism. And I was curious about why you think of it as a form of realism, but magical realism.
Well, first of all, I was making use of the literary
Exactly, I know.
magical. Yeah, I think that it's interesting because I haven't thought this through for a few months. The last time I had to teach this to good students, so and it's fairly subtle, so I have to think it through again. But basically, the problem is that the many worlds interpretation can be said to be that you just really remove rule one from the rule one, rule two distinction in the Copenhagen interpretation.
Oh, could you say what rule 1 and rule 2 are?
Yes. One way to present quantum mechanics, again, I think it's wrong, but it helps you get there a little bit, is to say that there are two ways that physical systems can evolve in the world. Rule one is according to the laws of nature as given by quantum mechanics Schrödinger equation. And these states evolving under rule one never collapse. They never do anything but proceed in what we would call a unitary fashion or a linear fashion. And that, of course, is not enough. That theory, based on just rule one, has no probabilities in it, unless you think you can derive them from somewhere. And that's why it becomes a big technical issue. So most people assume that you have to add on an additional rule, which is the rule for measurement, that says that it's basically Born's rule, that it introduces probability into the theory by saying that if you set up suitable circumstances where you can project out of the mathematics something that you're willing to call a probability, that it will satisfy the Born rule. And when I say it that way, because there are many different ways you try to define a probability, and the only one that seems to not be completely wrong is the Bayesian probabilities, which are, of course, subjective. We could get into that when we talk about mathematics. but the probabilities that many worlds people believe they're dealing with are definitely Bayesian probabilities. And then you get people saying all sorts of weird things about self-selecting themselves and worse, because they can only allow a subjective notion of probability into the theory. So you might not be too unhappy after you've done enough of this kind of stuff to consider just straight flat out realism.
Mm-hmm. Well, just one last thing about many worlds before we move on. This was something that really surprised me about speaking with Sean and David, was that I voiced what I think is the correct intuitive opinion that most people have, which is that what is most absurd about, on the face of it, many worlds is that we're supposed to entertain the possibility that there's this massive number of other worlds out there that we're not in any sort of causal contact with. But they told me that this doesn't bother them at all. What bothers them is just making sense of probability. Is that something that resonates with you as well? That's not what bothers you about many worlds? It's just the probability?
Well, let me make a comparison to Bohm, because it's somewhat revealing here. Bohm says that the wave function never collapses. Rule 1 is always satisfied. But there's a rule 2, which is different than the other version of rule 2. This version of rule 2 applies to particles. So we believe that waves exist on the configuration space, by the way, not in space-time. And we believe that also particles exist, and these particles satisfy equations of motion with respect to the waves that move around. Now, since you don't ever collapse the waves, and the same waves are there as any other form of quantum mechanics, in fact, Bohm has just as many ghost waves, you might call them, as anything else. The thing is that if you study how observers, which are both waves and particles, interact with the waves and particles that are in the usual quantum mechanics, you'll find that there's a whole universe out there of ghost waves, and there's just as many, and they're just as ghostly. Except that if you're a realist, when your system comes to make a choice or a measurement, you believe that the system consisting of the waves only goes out in its infinite number of directions, but the place where the particle is located in the wave function only goes one definite place. So you've got to believe that there is, if you adhere strictly to the mathematics of quantum mechanics, you've got to believe that there are an infinite number of ghost waves running around. And that's not fun either. I don't think that's...
No, I really enjoyed the discussion of ghost waves in the book. In particular, there was maybe a very apt connection to ghosts in that you discussed this time in your life where you missed or you rescheduled a plane flight maybe, and the plane crashed. So maybe one part of your ghost wave is a literal ghost maybe at the bottom of the ocean off of Canada.
Yes, and yes.
But so I think of magical realism as somewhere between realism and anti-realism. But when I think of anti-realism, the dominant view, especially still in the zeitgeist, is the Copenhagen interpretation, particularly because Einstein, so the prototypical realist, he sparred with Bohr, who was at the head of Copenhagen. And before we move on, how do the anti-realists like Bohr respond to what for us are these troublesome dimensions of quantum mechanics. So non-locality, entanglement, contextuality.
Yes, very well. Well, you should look at Bohr's example. I mean, Bohr is, I love to read Bohr. He's really means it when he says that this is not realism. In other words, what he says is the wave function is an extension of common language, that people, there has to be people, he's very Wittgensteinian, I think that's the word, in terms of that the purpose of science and what science is for Bohr is an extension of ordinary language, where people talk to each other about what they observed in their electrons and molecules and so forth. And the language that they use is supposed to have nothing to do with what's actually real in the system. It's language that you need to add on to your ordinary language if you're going to have a coherent discussion about what's happening in atomic physics. And Bohr very much situates it, and he comes from Schopenhauer, and he very much just situates quantum mechanics that way as an extension of ordinary language. Another person who you may or may not know from our contemporary world is Carlo Rovelli, who has been pushing a kind of extreme form of what he calls relational quantum mechanics. But if you follow him, he's pushing it much further than that.
Well, I know that Carlo is a longtime collaborator and friend of yours with loop quantum gravity and so on. And I was actually going to get to relational quantum mechanics a bit later, but since you bring it up, I was under the impression that relational hidden variables were something that you're very much in favor of.
Yes. Yes, but it's different than my friend Carlo's form of relational quantum mechanics. There are common themes that we share from the project in loop quantum gravity. Relationalism, as in Leibnizian relationalism, and we can talk about it, what it is the core of what Carlo and I do. It's the core to how we coded in the various technicalities in loop quantum gravity. And I turn left from somewhere there to realism, and he turns to what he calls relationalism. And of course, he says that he's a realist, but what he means by reality is quite different. And I think I'd leave that to him to explain.
Toward your realism and then maybe relational hidden variables as well, we've discussed now magical realism, we've discussed anti-realism, but how does quantum mechanics then, with its spooky actions at a distance and these other dimensions of, things that aren't so obvious or they don't seem natural to the realist, like contextuality, non-locality, and so on. How do they resonate with the realist? How did Einstein, for instance, try to make sense of them with his reasoning with EPR?
I was going to give you a beautiful answer until the last part. Can we skip to the beginning of the last part about Einstein? And let me tell you how I do it.
Absolutely.
Okay. So, because I really think the right way to present what I'm doing is as part of a research program which has several sides and is more ambitious than understanding quantum mechanics. That is, what we're interested in is getting the whole thing. Cosmology, quantum mechanics, relativity, unification. And let me have this go at getting the whole thing, because that's I think the right place where this kind of realism fits in. So we start with time, and in here I'm discussing the form of the theory as we developed with Clavier Verde. So in this form, we start by thinking of the world as consisting of events, and there are things in the world which are completely distinguishable or definite, and there are things in the world which are not distinguishable or definite. And we think of that as a realist part, placed apart. That is, there may be things in the world. When I speak of an observer, I'm always speaking of an embodied observer in the universe. So my situation with respect to something else that happens may or not be definitive. And I think that's just like, what does it call this? Intuitionistic logic, or
Right, the law of the excluded middle.
the law of excluded middle is gone, or think of things in terms of hiding algebras, which is the way that Fatima Lakakuda thinks of it. So I'm an observer somewhere caught in the universe, and I can cause events to happen. Events are situations or processes by which something that was indefinite becomes definite, or vice versa. And these things that become definite or indefinite are also not things of the whole universe. They're things nearby that I can manipulate somehow. Now, in this world, there exists, to start with, just these events and causal relations amongst these events. By a causal relation, I mean that if I make an event happen and take the result and put it into another event and put it into another event and so on, I'm going to have causal relations between, that is, if I see A from one detector and I see another output from a similar detector, it has to be, the result has to be consistent with each other. I'm maybe not saying that, but I want there to be a consistency between different results, which is strong enough to call it causal. Maybe we come back to that. And that's all I have in the world. Well, actually, I'm lying. That, plus I have energy, and I have momentum, and I have laws of conservation for them. So with two events send their output, which are energies and momenta, to a third event, I can rely on the summation of the two events to be conserved in how much energy they have. But I don't have position, I don't have momentum, I don't have angular momentum, I don't have a long list of other things you might have. My physics starts with the notion of what's distinguishable or not, events, and causal relations amongst the events. Okay, so if I have you with me.
You do. Identity of indiscernible. So we've got events we can discern. Then we've got causal relations between events.
Very good, and that's right. Now, let me be a little bit more. Let me tell you that in order to hold definite, in order to make the conservation laws work, I have to choose their forms in certain ways. And let me form the conservation laws of momentum and energy, first of all, to be additive. So if I have energy and momentum coming from different sources, they go out by adding them. I don't have to make that choice. In fact, there are choices of forms of extensions of general relativity where we make different choices. And I'll make the simplest one. And I also choose the relationship between energy and momentum consistent with special relativity. So E squared is equal to P squared plus M squared. Again, there is choices I don't have to make. And we have forms of the theory where we make different choices. So that's almost my full set of rules. Let me see which, okay. It's just a question of getting them in the right order. I have to choose how the events occur. So I'm going to have what we call the event generator. And we're going to have a number of events which just happened. And we're going to give us an algorithm to choose which next number of events happen. And let's keep that to be 2 events. So I have what I want to call the present events as ones that are just happening, and they send their output to a next event. And that keeps going on over and over again. Now, if I think about that, I have what I'll call now events. And now events have children, which are going to be the next now events. And I'm going to let cells impose that each event can only have a precise number of children. Let's call it 3. Once an event has had more children than the limit, it's no longer has any influence on the formation of the future. So we call those past events. Events that have not yet occurred, we call future events. And we do not impose necessary laws on the future events. That there can be a range of possible future events, and we have some algorithm that chooses them, but it doesn't necessarily choose them deterministically. So this system together is called an energetic causal set.
Yeah.
Okay, and that structure sits here, and now I'm going to derive some things from it. One of them is that I can make space emerge. That is, if I pick the other parameters and numbers suitably, I can show that there are little pieces of space or space-time that grow and have the geometry of Minkowski space or something near to Minkowski space. And that's a calculation. We can show you how to do that. Once I get space and time emerging, well, let me go. There's a lot of things that happen now. Let me go in the right order. Well, let me have everything set up in the simplest way first, so that I always get a correct what's my best word here? Immersion of space and time, of the events that I constructed into this model space and time. And so I can have emergence of space and time in a very pretty way while space-time is growing. So this is a point of view, this is why I told you I was a presentist. So we take this from actually Heisenberg, who had this. Heisenberg, it's not a very well-known part of Heisenberg, but Heisenberg at one point had papers in which he was discussing the fact that there's no reason to apply a wave function formalism to the past because you know what the past is, And therefore, first of all, it has no use anymore. Once you know it, it's useless to you, except for making a few more events to keep the thing going. And events in the past, therefore, are definite, and events in the future have no meaning yet. So we really just need a universe which consists of a bunch of finite present events. And so that's the direction our cosmological theory is going. Maybe I should stop there. There's a bunch of other stuff, but maybe I should stop there.
No, that was all great. And I have a number of comments and questions. The first thing, though, is just to mention it. You said that you described this framework as energetic causal sets. And I'm talking to Faye Dowker tomorrow all about causal sets. So this is great timing. Because as you were thinking, as you were talking, I was thinking, yeah, this is just like the constant birth of new space-time atoms, as a causal set theorist would put it, I think. And one thing worth mentioning, I've already talked about or mentioned Einstein's Unfinished Revolution, but I read another book of yours called The Singular Universe and the Reality of Time that you wrote with Roberto Mangabeira, Unger.
Mangabeira, Unger, yes.
Yeah, who is a very distinguished law professor at Harvard University. And the reason that I bring this book up now is that a lot of this work that you've just discussed is gone over in great depth in this book with Roberto, as well as its philosophical motivation. So I thought I should ask you just a bit about that project, because it's quite a unique book.
Yes, and it was a very difficult project. Do you know Roberto?
I mean, I don't know him personally, but I've seen his work, his legal work.
He's very, very smart. We can start there. If you'll give me the space to tell the story, I'll tell you how I met him and started working with him.
Yeah, you have all the space you need.
Okay. Well, first of all, long before I knew him, he was a young law professor at Harvard when I was a graduate student. And I knew of him because there was this legendary leftist, intense, dedicated law professor who you could see to all hours of the day and night in the Radcliffe Library with his piles and piles of books and papers around him. And later I had a student who was a graduate student at Harvard, this is after I'd moved on, who had a wife who was his student. And then I heard about him a third time through my brother, who was a legal theorist and now a law professor. And David was very much in admiration of him. And then finally, a friend of mine from a long way back, who just unfortunately died recently, Drusilla Cornell, was a friend of his. And Drusilla was many things. She was certainly a law professor, a playwright, a writer in many different aspects of feminism. And she was one of the readers on my first book. And she called me and she said, there's somebody in my world this is my first book, which is called The Life of the Cosmos, and is about laws evolving and changing in time. And she said, I have this colleague who has the same idea and is thinking about the same idea. So now I'll compress a long story. And at some point, I ended up on the phone with him, and he said, why don't you come up to Harvard and have a chat? So the next time I was there, I knocked on his door, and we had a 4-hour chat. Now, Roberto I think now I know him and we're friends. I think of him as a very sweet person. And he is indeed a very sweet and kind person, but he's certainly terrifying on first meeting, especially if you're not remotely in the same area as him. But we talked about what we had set out to talk about, which is why we each thought that the laws evolve. And then he said a couple of remarkable things. The first thing he said is, I've been thinking these thoughts for 20 years about changes of laws in physics, but I've never actually met a physicist. Do we have any physicists here at Harvard? And what's even funnier about that is that the law school sits on the law school quad. I don't know if you know it. And the physics building sits on a corner to it. So who knows if you've really ever met another physicist, but I believe it because he's not somebody who goes except very selectively and meets people. Anyway, then he proposed we write a book together about this common theme. And that was, we started out, each of us writing, we outlined the chapters, as you will, and each of us took half the chapters and set out home to write them. And then before anything else happened, he got appointed to the government of Brazil as the Minister of the Future, which meant if I was to have any time with him, I had to fly to Brazil and sort of shadow him around in his government post. So it went slowly. But as we developed the book, we realized that the things that we had agreed about in the outline were about the only things we agreed about. And that he hated my writing. And he said so every chance he got. He said, come on, you mean to be read by serious philosophers? And I would say yes, timidly. He would say, well, serious philosophers don't write for other philosophers. And they don't care about their audience. They write to be true philosophers. And conversely, I would call him and say, Roberto, do you expect anybody to read this stuff? And he said, well, maybe in 300 or 400 years. And he meant it and means it. And he's this peculiar to me. I mean, I love him very much, but he's a peculiar combination of enormously energetic when he gives a presentation in any forum, whether it's politics or a law school class or some academic thing. He makes no notes. He walks out on stage with nothing, and he speaks in perfect sentences and paragraphs for exactly the time you've given him, and sits down. And he's a brilliant orator and brilliant speaker. But for some reason, when he writes, it doesn't happen. It's hard for me to read him, although now, of course, I can. To read him, I discovered you have to read him standing up, and you have to take a lot of breaks. So anyway, that's how the book evolved for a number of years. And then we said, look, we had an editor by then, which is in Oxford, but there's nothing we can do. Let's just call up the editor, and either we can deliver him both books, and he can print them side by side, or we'll just have to drop it. And Cambridge University Press was nice enough to print both books.
Well, you mentioned this exchange a couple of minutes ago about whether anyone would read the book, but I mean, I read it and I loved it. There were three things that I most appreciated about it, and that was one, your explanation of the role of the Newtonian paradigm in cosmology and why it needs to be abandoned, and then an explanation of the radical presentism that we just described, and then third, your thoughts on the foundations of mathematics. Granted, I just mentioned, let's see, the Newtonian paradigm, the radical presentism, the foundations of mathematics. There's actually something that I wanted to ask first about, because I think it's particularly relevant, not just for the program you described, but for some of the material that's been discussed on the podcast recently. Because like I mentioned with Sean Carroll and David Albert, we talked about fine tuning, and fine tuning has come up a lot. And many of the physicists that I've spoken with, particularly string theorists, have endorsed multiverse accounts of cosmology to account for fine tuning. So one of the most important, I think, bedrocks of your work with Roberto that you do agree upon in the introduction is something that you refer to as the principle of the singular existence of the universe. So I thought maybe I might ask you if you could explain this principle.
Well, it comes directly from Leibniz. And the idea is that we want to force ourselves to think. Hold on, I just did. If you ever have to take pills every 3 hours, don't tell your family. Because everybody comes in a row to line up to tell you. It seems to me, I know there's an argument, and we'll put together the argument if you want, but the vision of a universe that we want is one which has as much variety and, dare I use the word, freedom in its construction. And it's very different. I think we cosmologists get into a bad habit early in our careers of playing with model cosmologies, which have lots of symmetries, lots of regularities, and not much variety. So we always study cosmological models like Freeman Robinson Walker, which are perfectly round or perfectly toroidal or something like that. And those models, they are solutions formally of the Einstein equations. But if you actually give a really correct version of the Einstein equations and ask what they apply to, the solution set lives in a space of diffeomorphism in variant states. And diffeomorphism in variant states are those that every neighborhood of every event or point can be distinguished from any other one by observables you would be able to measure or observe near every point. So the Schwarzschild solution, the other solutions I've been mentioning, just don't mean anything. They're not part of the physical theory of general relativity for the cosmological case where you have closed boundaries and you have no asymptotics. And that's just true. And it's been true for, Einstein understood that. And it means that we rule out all the solutions that we got used to studying are models which have no physical reality, and in a way that matters very much. And I think that's done tremendous damage to the practice of theoretical cosmology. So, and we can talk much more about that, but I think it's essential to start with that point. So, for example, when 90-something% of the papers by my friends, and they are my friends, string theorists, are about solutions which have a certain symmetry called asymptotic anti-de Sitter. And those solutions do not exist in the state space of real solutions to general relativity. So it's a lot of bad habits have evolved, and bad habits of thought, where people use these non-existent solutions as examples.
Does this relate at all to your position on the foundations of mathematics and the role of mathematics in physics? Because one thing that I picked up on reading is that you think one of the ways that mathematics has been so important to physics is that it provides this huge space of models that can mirror physical reality.
Right, but you've got to be careful that your space of models doesn't. I mean, the problem is that the diffeomorphism invariance is not a small thing. The theory of general relativity has no solutions, cannot be solved, is not consistent mathematically unless you restrict it in this way.
Well, maybe more explicitly asking or moving towards the philosophy of mathematics. I don't recall ever reading a physicist who felt that having a very well spelled out positions on the philosophical foundations of mathematics was so important to an ultimate theory of cosmology. But here it is, I mean, front and center in your work. Why do you take it as so relevant to a theory of cosmology if, on your view, mathematical objects don't have a physical existence?
Well, first, thank you. That's a huge compliment. And I'm certainly not done. That's the first thing. The second thing I ever write related to the foundations of mathematics. And I've got a long way. I mean, I have, of course, an independent interest in the question. And the questions of foundations of mathematics are very interesting to me in general. And to try to work out some sort of position, let me call it very much a first position on the foundational questions in mathematics is very interesting. And they're hard questions. They're really hard questions. But I don't think that the right answer is in the ballpark of Platonism. And one way, I mean, this is when we were working with Roberto, and this is a thought, one morning in passing during that, but I think it's had a big influence on me. What I think many people in physics used to believe is that what's his name called the mirror of reality, that there was a mathematical system in the sense of a system spelled out by a list of assumptions, which had a one-to-one correspondence with physical reality. And our job as scientists was to discover this object in mathematics that had the one-to-one relation to physical reality. And what occurred to me is that there are objects, and you can think of a few of them, which cannot possibly have a one-to-one relationship with an element of physical reality. And one of them is the notion of time as something that is real and continual. So you seem to have a choice there between being a realist about time or being a Platonist kind of realist about mathematics. And I told Roberto, and he said something like, "I thought you knew that." but I think, well, I'd love to speculate, but And I did in the book, it's true, there's a whole chapter where I try to work up a kind of a way of talking about what events are. And maybe we could go about them. Well, I guess I'm scared. It's hard stuff. But I
To talk about what events are?
well, just what mathematical. Yes, but also what physical.
I see.
What physical events are, sure.
Mm-hmm. Am I right, though, to think that one reason that having a well-defended position in the foundations of mathematics is important for your project in particular is that Platonism, if it's a coherent position, it poses a threat to the principle of the singular existence of the universe. Because if there is this mathematical realm of objects, then the principle of the singular existence of the universe goes out the door completely.
Yes, and Roger Penrose's view is well in contradiction with this. I mean, Roger is a sort of three-time Platonist. And Roger is one of the people I respect a lot. This fits in with, I'm looking here at the trees in the park out the window. There's another part of the whole period where I've been looking at these questions has been a different collaboration with some people, and I'll tell you who they are in a minute, working on sort of philosophy of biology kind of questions.
Oh, really? Stuart Kaufman,
yes,
is that one
Stuart
of the people?
Kaufman, Marina Cortez, and Andrew Little. We published 4 papers together, sort of about this, sort of 2-3 years ago. And we're interested there certainly that work is also very incomplete, but we're interested in the idea of, well, whether you can, one question is whether you can meaningfully count, say, the number of biological species. So if you want to make arguments about, is the world full of life? Is life just a little bit? You have to learn to count whatever you think life is. And we spent a lot of time thinking about that.
You spent a lot of time thinking about what life is?
Certainly, yes. And we have...
Well, this is totally a divergence from what we were discussing, but I'm very curious if you came up with you said it's work in progress, but if you have a hunch about what life is, because I don't know, I'm of the mind at this point that it's not really I mean, it might be useful for humans to have a working definition of life, but I'm not sure it's something that really cleaves the world at the joints, so to speak, the way that electrons are quite definitively a category.
Oh, no. Well, here's one way we get into it. Supposing you wanted, let me think of the best way into this. One minute. Supposing you wanted to count the number of biological species that would be on the Earth in 1 million years. If that's part of science, it's something we ought to be able to do. Let me make the question simpler. Supposing you wanted to count the number of proteins on the Earth in 1,000,000 years. Well, how would you do it? And the problem is that which proteins stay around and evolve are functional ideas. And so you have to be able to speak in sort of formal or definite language about what is a species, and you have to somewhere use a functional argument. Now, here's one reason you have to use a functional argument. If you just count the number of species made out of chains of what am I wanting? Sorry, not polyhedra, polypeptides. Then there are something like 2 to the 20 or 4 to the 20 different polypeptides possible as used in possible species on the Earth. And that's vastly more than the number of kinds of proteins that we have on the Earth now. So we have to explain why it is that a very small fraction of the proteins that might exist do exist. And I'm afraid I would be better at this after looking at it for a night, but that's the kind of thing that we discuss. But we have these 3 papers out on the archive about it.
Well, this is a topic for another time, but one that I'm very interested in. I've had a few conversations recently about what life is and how we can define it and make useful definitions of it. But for now, this was so terrific. Thank you so much for joining me. I mean, your work sprawls, as we just heard in the last few minutes, in so many different directions. But I'm looking very much forward to future conversations where we can get into detail on these individual topics.
Yes, absolutely. And yes, thank you. You know, it's if I can comment on the disease, which you see, it's a very strange disease to have because you vary not just in the course of a day, but in the course of an hour significantly. And I am a cyborg in that I have electrodes in my head, and that does part of it. And that raises a whole other set of issues, by the way. That is, I am an instance of somebody who has a computer in their brain, and there are not a few of us at this point. And it's also just weird. I mean, if you have some standard rare disease, then you're at some point and you get worse. And unfortunately, sometimes you get better, sometimes you get worse. But for me, it's every day is like this. And in an hour or two, I'll be bright and cheery and bushy-eyed again. Which makes it an interesting way to live. But
yeah, I'm sure it's very difficult, but it's also a new journey in a way. I guess that's probably how you look at it.
Yes, and one very much doesn't know where one is going. That is, there are typical symptoms, but there are no general symptoms. There are people with the same label have very different diseases. And
I'm wondering if you'll permit me a question about it. Does this sort of new constraint on your life in any way lead to different ways of approaching your work? in positive ways that weren't there before?
I'm looking for them, certainly, all the time. But first of all, I do work, and that to me is an achievement. That is, I can organize my life. I have helpers, which I'm very grateful for. And I can go to work and back to work and work with students and write and so forth. I just have to plan it a bit more. But, and it's certainly, it's all those things that you say, but it's really true. It's when it's learning all the time and one wants to stay positive, and there are reasons to. And maybe I'll just leave that as a little thing. I mean, think for a while about what it means to have dopamine flooded through your system all the time. So.
Well, again, Lee, thank you so much. Hold on. If you haven't subscribed, liked, commented, or reviewed, that would be so helpful. And if you haven't yet, you could also follow me on Twitter and Instagram at Robinson Erhardt.